Good afternoon, everyone. This is work that spans quite a few years and many people. We've got this ANFF-supported polymer fibre capability, and lots of people come to us with interesting requests to make fibres. So I'm going to go through quite a few of these, and that means that I won't be able to go into much in depth, but if you want to know more, come and speak to me. I will be on the ANFF booth in the exhibition, and we'll have some samples there. And I won't be able to credit any all of the people involved. I will point out that this is Justin Digweed, who is our ANFF-funded fibre fabricator. So the idea here is I want to talk about the fabrication of these fibres. I'll start off with just very briefly fibre fabrication. I think if you've been in this session for the whole day, you've seen this earlier. The various types of fibres, the way they're developed sort of overlap, so there's no really obvious sort of linear flow through them, but I'm going to start with microstructured polymer optical fibres, then look at metamaterials, basically filling the holes in these air-hold fibres with metal, then go to fibres which have a combination of wires, waveguides and fluidic channels, and then on to a couple of biomedical applications. So my intention is to, most of the fibres I'll talk about are polymer, but not all, and largely they're microstructured fibres, but again, not all of them. So I'm intending to give some examples of how they're used, examples of the fibres themselves, how they're used, and what are the sort of the fabrication aspects of them. So fibre fabrication, I guess this is familiar from earlier talks. What we've got is a preform where you make the structure on macro scale, put it in a furnace, wind it around some capstans and onto a spool, and hopefully you get the same structure in the fibre as you had in the preform. This is the slide that you've just seen in the intro. So this is the furnace here. Glowing here, you can see the preform being fed into the furnace. This is a two-story tower, so that's the top half of it. This is the bottom half of it. The fibre drops down here around this capstan and wound onto the spool. So that's the capability we've got up at Sydney as part of the ANFF New South Wales node. And this is a typical process, just to give you an idea. There are so many variants on it that it's really hard to be definitive about this. Typically, we use a two-stage process where we make a macro scale preform, maybe sort of 10 centimeters size, draw it down to a cane, roughly a centimeter, and then draw that down to fibre. Sometimes we go directly from one to the other. The important thing is how you create the pattern in here. This is showing us using a CNC mill, drilling a whole series of holes. We can also use stacking, 3D printing. Historically, we did a lot of work with drilling. These days, typically, we'll use a stack and draw process, which was described in one of the earlier talks. So this is a rogues gallery of some of the interesting microstructured polymer fibres that we've made. I'll talk about a few of these in a bit more detail. But one of the benefits of using polymer over silica or glasses is that it's a much easier material in general to work. If you want to machine it, you've got to go to some quite exotic material to drill holes in silica glass. Drilling holes in perspex is a lot easier. So it's a lower cost, easier way of realizing some really exotic structures. So here's some examples. We made some single mode polymer microstructured fibre. Those regular arrays are very easy to get in stack and draw. You've probably seen those earlier. The interesting thing we could do with polymer is it's much easier to stretch it. So we made some long period grating strain sensors with this. We also have made twin core single mode fibre, and this is a double clad fibre with a single mode core in the middle and a large high NA multi-mode core around it. This one is really cute, graded refractive index multi-mode fibre. This pattern would be pretty hard to make by drilling, by stacking or by extrusion, I think. Pretty much only amenable to this approach. And it isn't obvious what's going on here. If you took the azimuthal average of that, what you're getting is a nice graded refractive index profile, which then means that you can make a graded refractive index profile multi-mode fibre out of a single material, which is kind of interesting. When we realised we could do this, we were really excited. We thought it would change the world of datacoms. We got us a paper, but no one seemed interested in licensing it, unfortunately, even though we still, I believe, hold a bandwidth distance product record for a polymer fibre. We can also make hollow core fibre. These were very sort of exciting when the idea first came out of having a photonic band gap. What this one shows is that as you draw it to different sizes and the spacing in the holes changes, the colour of the guided light changes. So photonic band gaps fairly readily realised in these materials. And this shows a couple of other hollow core structures. This is a sort of a segment out of a larger fibre. These are air gaps. So what we've got here is essentially a Bragg fibre with concentric rings of high and low refractive index. Again, that's probably a hard thing to make from other approaches. So that's the microstructured polymer optical. Yes, we've used them in various things, optical applications in datacomms, imaging, and sensing. So I now want to skip directly to metamaterials. And despite what someone said earlier, I think the meta optics are better than metamaterials. Why are metamaterials interesting? They give you the ability to control some very basic parameters. You know, nature gives us all these materials, and something about them is set. You know, the permittivity and the permeability, they control the electromagnetic behavior of these materials, but they are what they are. Metamaterials gives us the ability to modify these, and you can get values which are really quite different from what nature gives you. If you can make something with both negative permittivity and permeability, you can make negative refractive index, which is something that doesn't occur naturally. And if you can create these really exotic properties, then you can make devices with extraordinary functions. So invisibility cloaking and hyperlensing and so forth. So I hope I've told you why those metamaterials are actually interesting. What are they? So the most basic structure looks like this. They are sub-wavelength structured composites, and typically they're metals and dielectrics. So what I'm showing here is an array of very fine wires with precise spacing embedded in a dielectric. And if you look at that, it looks rather like one of those microstructured polymer optical fibres, but instead of having an array of air holes, it's got an array of metal wires in there. And I'm going to put some maths up, but I won't talk about it much. So we're interested in controlling in this the permittivity. It depends on this. There's one key parameter there, the plasma frequency, and that's essentially the boundary between it behaving as a dielectric and behaving as a metal. And if you look at what determines that, it's largely the geometry. So the spacing of the wires and the diameter of the wires. So that gives us a fairly straightforward way of making one of these metamaterials and controlling permittivity or plasma frequency. And it looks pretty much like a microstructured fiber. And when you look at the dimensions that you can typically make quite easily in these, it corresponds to terahertz frequencies. And we heard recently why they're interesting. So our approach was to take our standard polymer microstructured fiber approach and adapt it by putting indium in the holes in a PMMA preform and then drawing it and then cutting off short lengths of it, because even though this is using fiber drawing, we're not generally launching light into it as a fiber. So this shows a cross section there. The little bright spots are the indium reflecting in the microscopes, showing we can get a pretty good ordered array of those. So we took these short segments, lined a whole load of them up. So we've got a planar structure of a metamaterial, and we exposed that to a terahertz time domain spectroscopy system, and we drew them to several different sizes. And without going into too much detail here, this is showing the transmission versus frequency. Low transmission means it's acting pretty much as a metal, high transmission as a dielectric. This is the plasma frequency, and you can see that we've tuned that over a couple of orders of magnitude. So we can control this basic parameter permittivity. Permeability is interesting. This is what governs the magnetic properties, and nature isn't very kind to us with natural materials. Pretty much every optical material has got a permeability of about 1. So it would be good to be able to tune that. And you need to use a much more exotic structure. You've got to have some ring structure because the electromagnetic field has got to drive a circulating current. So we went to great lengths to rather than use wires to make these sort of split rings or split cylinders. And without going into much detail here, we managed to tune the permeability from about, I think it was -3 up to +4. So there's a way there of using this approach for tuning those basic parameters. So that's nice. We've modified some fundamental parameters, that we should do something with it. And of course, it would be really great to make an invisibility cloak. That would have a huge impact, but that is so difficult that we didn't think about it for more than a short while. What we settled on was a hyperlens, which is much more practical to realize and is still pretty cool. So if you know your optics, there's the classical diffraction limit. It's with, there are tricks you can play, but basically the rule of thumb is you can't focus to smaller than half of the wavelength of the light that you're using. So if we look at one of these wire arrays, and previously I was showing light being put through the transversely through it. If you now launch light in from the top, an interesting thing happens. You get propagation without diffraction on one of the polarization states. And that's because as it tends to diffract, you'll end up with a component along one of the along the wires, and that can't propagate. So you can put light in at one end, and it will come out without diffraction at the other end. But that doesn't really give you much. That just gives you, the same thing out as you put in. What's interesting though is if you taper this, because the taper is slow compared to the wavelength. So essentially, it just squeezes the transverse light field down in the taper rate. And this is, if you think about fiber drawing, you've got this taper naturally occurring as you in the furnace. So we made one of these, and this is some X-ray tomography showing the structure of the wires. The dielectric isn't visible there. This has 500 very fine indium wires in a 38mm long taper. This is the input face, and that's the output face. So a bit of a hero experiment in terms of how to make one of these devices on a draw tower. And we put a 1mm aperture on the input, but using radiation at 75 gigahertz. So this is quite a long wavelength compared to that aperture, and then we focused it down. It could take a long time to explain this slide in detail, but the key thing is the polarization state here. We've squeezed the light down there to 1/28th of the wavelength. So beating the classical diffraction limit by over an order of magnitude. We went on to push this a bit further and got down to almost lambda by 200. So it is a way of getting well below the or sub-diffraction focusing. So in terms of the fabrication, this has been a combination of dielectrics. Mainly we use a cycloolefin called Xeonex, really because it's got very high transparency in the terahertz region. And the metal that we put in there is indium. This gives an idea, around 500 wires, 50 micron spacing, 10 micron wires. And the question, I guess, is why use indium? And that's because we're using something called the Taylor wire process. So in the draw, what we've got is the metal is molten at the temperature that the polymer becomes viscous and starts to shrink down. So there's not many metals that are molten at those sort of sub 100, 200 degree temperatures that this will work for. So indium is reasonably widely used technologically, so we chose that. There is a problem in terms of how small you can go with this, because you get this problem of the Rayleigh plateau instability, and your nice fine wire breaks up into a series of droplets because of the surface tension between the two materials. My only mention of glass is to say we wanted to push this a bit further. So we went to tin and soda lime, which work together a bit better. And this shows one with 250 nanometer wires and a large array of them. So it's an interesting way of making regular arrays of very fine wires embedded in a dielectric, if that's something you're interested in. Okay, so having started putting wires into dielectrics and had made some cute metamaterials, we thought this was something a bit more practical and that we can do with this. We started looking at the possibility of neural interfaces. We've got some colleagues who are working in optogenetics, where they transfect cells so that they're optically sensitive, and being able to get in a light signal and an electrical signal for stimulation or detection of neurons seemed to be a cool idea. So we made this thing here, which has got a central waveguide and then 4 sets of 4 electrodes embedded in it. And if you're squeamish, don't look at the next. Actually, no, the next one's okay. This is just showing the fan out from the far end. And we tried it in a mouse's brain and did get the ability to detect neurons firing. So squeamish people look away for 5 seconds, just showing that we actually did that. So in terms of the fabrication, that initial work was done with indium. And indium, whilst it makes it easy to fabricate, is not terribly useful. The biologists would prefer to use other materials like gold for interfacing with neurons. It also causes a problem in the fan out because it's a very soft metal and it's pretty hard to deal with when you've got very fine filaments of it. So we moved to drawing hard wires, and these are some pictures of the fan out with hard wires and a microscopic or micrograph of hard wires coming out of the end face. How we do that, because we can't use this Taylor wire process where the metal shrinks down, is we start with very fine wires on spools, a guide, and then they go into the top of the preform. And as the preform shrinks in the neck down region, it collapses onto the wire, grabs it and pulls it through. And that works reasonably well, but unlike the 500 wires we got with indium, it has limited scalability. This is quite a contraption, and the more wires you add, the more spools, the more chance something's going to snag and break. So we wouldn't really want to take, that's got 12 wires in it. I don't think you'd really want to scale that up much more than that, but it is a good way of drawing in high melting temperature metals, things like tungsten and platinum and so forth. Also, it may not be obvious, but this is, well, I guess it is, it's black, it's not shiny. It's actually not metal in this case. This image is of carbon fiber. There was an interest in having things which were still conductive and much more flexible than, say, tungsten. So we can draw multiple filaments of carbon fiber into polymer fibers. It's not a very well controlled process at the moment. You get something which is quite often lumpy because the carbon fiber yarns are not as smooth as as you can get very fine wires. Right, so where do I go next? Yes, optical fibers for sensors. So just going to a bit of physics, the important thing if you want to do mechanical sensing is the Young's modulus of the material. This governs the amount of strain, the amount of stretch that you get for a given force or stress that's applied to the material. That's the Young's modulus is then critical for, if you want a very sensitive sensor, you need a low Young's modulus, so a small amount of force gives a lot of perturbation. The other thing that's important is the breaking strain. You can't continue stretching something without it breaking. And so those two are quite important for sensing. So looking at some materials, silica, which we all know and love and makes most optical fibers, has a high Young's modulus approaching 100 gigapascals and a very low breaking strain. Stretch it more than 1 or 2% and it breaks. We all know that glass is hard and brittle. PMMA perspex is a bit lower Young's modulus and a bit higher breaking strain, but polyurethane is really quite interesting. It's got a much lower Young's modulus, 4 or 5 orders of magnitude, and a very, very large breaking strain comparatively. Some polyurethane you can stretch by a factor of 6 before it'll break, which is why it's good for making slingshots and rubber bands and spandex and things out of. The other thing, when you're looking at sensors, especially sensors for wearables and to do with the body, is how it compares to the material that it's sensing. So this gives a range of Young's modulus, this time in kilopascals, not megapascals, for things from fat through to bone. And polyurethane sits somewhere in this region. So it's mechanically compatible with some body tissues. So that drove us to think, well, can we make very low Young's modulus polyurethane fibres, taking benefit of the fact that the stiffness is much less than silica, giving greater sensitivity, and that the breaking strain is much greater, and then use those in wearable health monitors. That was our idea, and we sure can draw some reasonably complex structures. These are about millimeter scale. I've got one here, and to demonstrate it's got properties very, very different from a standard optical fibre. You can certainly stretch it a long way before it breaks. So the first thing we did was a respiration sensor. We embedded, arrows on this, a standard elastic bandage, one of these fibres, a laser diode. You can see a little bit of red glow there, and a detector. And we got this guy to run on a treadmill. This is him at 7 kilometers an hour. And there's certainly something going on there. But there's more than one thing going on there. When you take a Fourier transform of this, you get several peaks. That first peak corresponds to the breathing, about once every 4 seconds. The second peak, interestingly, corresponds to his footfall, measuring his gait. Knowing that he was running at 7 kilometers an hour, that was how regularly his steps were happening. So with a very, very simple system, we were able to pick up 2 physiological things there. The other peaks are just harmonics. So that was cute. I'm not sure that it will change the world, being able to integrate into someone's shirt the ability to measure their breathing and how fast they're walking, but it could. But we looked around for something which was a bit more significant in terms of a problem, and decided we'd try to make a blood pressure monitoring wearable. And the approach to this was to use 2 of these fibres placed across, if this is the radial artery on the wrist, 2 of these, and without the equations here, but basically, if you can get the timing there, then you can get the velocity of the pulse going through the artery, and with a 2-point calibration, you can then get to the blood pressure. So this shows. Is this a video? No, it isn't. This shows some live measurements there. They're inverted because the way this works is the loss increases as the fibre is pressed by the pulse going beneath it. So this shows a couple of traces there. We're getting things which look very much like we would expect. That's sort of out of a textbook of what a pulse should look like. So with these very simple, very rugged optical fibres, we've got a way of really quite sensitively picking up. If you put your finger on your radial artery, it's not a huge pressure there we're picking up, and we're picking up with a good level of resolution. So we also had a look at whether we can make electrical sensors. I'm going to skip quite fast through this. We just embedded a couple of wires into a couple of these air holes in the polymer fibre. Here's the micrograph of that being squashed, and it can be squashed many times and bounces back. And you can get a nice, by measuring the resonance and basically changing the capacitance, you can get a good measure of the compression distance. And if you use 3 of them, measure all of the different capacitance changes. You can get a sensor which gives you not just the pressure, but also the direction of the pressure. Possibly cute, we've not found a use for it, but it was very simple to do. Right, tunable metamaterials. You've seen this before. If you recall, the plasma frequency, the properties depend entirely on the geometry. So once you've drawn it, you're stuck. You've got something which has got fixed properties. But we've just shown that we can draw very, very soft polymer materials. So we did this, and these are pretty ugly because polyurethane is not an easy material to draw, especially if you've got metals embedded in it. But we drew the structure, and we can easily squeeze it, and it bounces back reasonably well. And the interesting thing here was we tuned that plasma frequency over about a factor of 2. So a good way of, well, a demonstration of a tunable metamaterial, shall we say. And I think I probably need to wrap up very soon, don't I? So I will skip very fast through this. We've also been drawing polycaprolactone. It's a resorbable polymer, and have been using this with a view to tissue scaffolds. So plasma treating, so we can surface functionalize, stick growth factor on, put it in stem cells, and use that for guiding the cell differentiation as a way of building up a structure which would then be implanted for someone who's lost key tissues through trauma or disease. Preform, you can draw it into fibre, and we have grown all 8 of the cell types that are present in the bone marrow niche. So it works. There's a long way to go, but it's another type of fibre that we can draw. So I will wrap up with a summary. We can draw multi-component fibres, holes, polymers, glasses, and wires, a whole range of insulators or dielectrics, polymers and glasses, hard polymers, soft polymers, bioresorbable polymers, and some soft glasses, conductors, so low melting point, indium, tin, etc., high melting point by a different technique, and carbon fibre. That has an issue with scalability. And I think that's my last slide. So thank you for listening. Thank you for fun.
Thanks very much, Simon. Very useful. I'll just take one quick question, and Simon will be there also in the next 5 days at the ANFF.
Yes, and I'm happy to talk afterwards, but yes, come to the ANFF booth in the exhibition.
Yeah, I'll just take this quick question.
So is it easier to bend them into very small radiuses of curvature then?
Well, I can tie a knot in this, but silica fibre, when you've got it coated, you can take it down to about 1 millimetre bend radius. Silica is actually quite strong. It's just surface imperfections will cause it to break. But yes, we can take them down quite small. There are some tricks because the guidance we're using for these polyurethane fibres is capillary guidance, and that isn't very good at small radiuses.
Okay.
The fibers were separated by 6 centimeters, I believe.
30 or 32 millimeters. 3 centimeters, roughly.
So can they be 1 centimeter apart so you can?
Yes, they can. The velocity is something like, I think it's 8 meters per second, roughly. It varies between people and how, which means that the timing difference at 3 centimeters is something like 4 milliseconds, I think. So the problem then means to get an accurate measurement, you've got to be able to detect that to sub-milliseconds, and that starts to become very difficult, especially when you've got other factors in there. I'm giving a talk on this in the main, I think on Tuesday in the WSOF, was the ANZOS session, I can't remember. We have made these sensors where we measure on the wrist and on the ankle, where the separation is much greater and it works fine. On the wrist at that distance, whilst we still get beautiful signals out, the timing is we just can't solve this at the moment to get accurate measurements.
Thanks very